Hi everyone, welcome back. In this particular video, what I'm going to do is I'm going to walk you through some examples of completing acid-base reactions and then determining the favored direction at equilibrium. But what we're doing is a qualitative analysis. So the two examples that I've chosen for this video here, the first one is the reaction of this molecule here with NaOH, sodium hydroxide. Okay. Now, in this particular case, I think because sodium hydroxide is a known base, we can qualify this as the base, and which means that this molecule here must be the acid. Now notice how sodium hydroxide is written without any charges, but these are things that we would be required to do at this point. So what we know is sodium hydroxide is basically Na plus, and this is an OH minus. So the hydroxide oxygen has a negative charge on it because it's an ionic compound. So even if the charges are not shown, you would be expected to know that there are charges here. Okay. On my acid side, there are several hydrogens in this molecule here, but the hydrogen that's connected to this oxygen must be the most acidic here. And so what I'm going to do is I'm going to draw it out so that I can show the electron push for my acid-base reaction. Okay, so once I have set it up, what I can say is that what happens is the base goes and abstracts the proton from the acid. Electrons from this bond between the oxygen and the hydrogen simultaneously move to that oxygen atom to maintain octet around the hydrogen atom. And so what I would get on the product side are my products here going to be this molecule with oxygen that is negatively charged, and when hydroxide picks up that hydrogen, it's going to become water. That oxygen has 2 lone pairs to it now. It had 3 lone pairs here. I haven't shown that, but that is already implied. Okay, so acid, when it loses its proton, becomes the conjugate base. And when the base accepts a proton, it becomes the conjugate acid. And what I've missed here is the sodium ion, which must be with this benzoate. That's what we call it. That's the benzoate. You are not required to know the name at this point, but that's a benzoate. Okay, so the sodium is balancing the charge along with the benzoate. So we've completed our acid-base reaction. The next thing we have to do is we have to determine the favored direction at equilibrium. That means we have to predict whether this reaction is favored in the forward direction or is it favored in the backward direction. And so to do that, what we have to do is we have to analyze the strengths of the, or analyze or compare the strengths of the 2 acids here. Okay, there are 2 acids in this equation. One is the acid itself, the other one is the conjugate acid. Now, to compare their strengths, so when we say strengths, right, we are talking about acidity. The question here is which one of these 2 acids between the acid and the conjugate acid, which one of them is the stronger acid. And so now to determine that, we have to consider the conjugate base of these acids. So if I consider this acid, its conjugate base is this molecule here. Okay, so you're comparing stability of the 2 conjugate bases, essentially. Okay, there are two conjugate bases, and we're going to compare the stability of those two. So which are the two conjugate bases? For this acid, the conjugate base is this molecule. So that's this molecule here. That is the base. We can leave out the sodium. That is part of the base, but it's pretty much balancing out the charge. So that is the conjugate base. And for the conjugate acid here, which is water, the conjugate base for it when it loses the proton is this base here. So it's a hydroxide. So you're comparing that this benzoate versus the hydroxide. Which one of these is more stable? Okay, that is what we are comparing here. So now if you look at the two conjugate bases, the negative charge is on an oxygen atom in both. Okay, in both cases the negative charge is on an oxygen atom, but this conjugate base can do resonance. Okay, there's resonance possible here. And there is no resonance possible over there. And because of resonance, this conjugate base here should be more stable because we have spread out the charge, or we delocalize the charge. So this is more stable. The benzoate is more stable. So of the two conjugate bases, we have determined that this is more stable because of resonance. And this is less stable. Okay, now if this conjugate base is more stable, what that means is this acid here, its corresponding acid, must be the stronger acid. And since this is the less stable conjugate base, this acid here is the weaker acid. Okay, now if this conjugate base is more stable compared to the other conjugate base that we are comparing it to, okay, when compared, if this is more stable, that means it is less likely to accept protons compared to the other one, okay? Or what we can see is this is a weaker base, okay? And since this is less stable base among the two, what that means is this is a stronger base, okay? Because it is less stable, it does not like to have that negative charge on the oxygen. Again, it's a relative situation compared to the other base. So this is less stable, okay? This is less stable, and so it does not like that negative charge. How could it get rid of the negative charge? It could accept a proton. And when it accepts a proton, it is acting as a base, and it would get rid of the negative charge by accepting a proton. So essentially what we notice is here is our analysis is complete, and what we figured is that the strong acid and the strong base, they are both on the left-hand side here, or on the reactant side here. The weaker acid and the weaker base are on the product side. And so what that means is this reaction is favored in the forward direction, okay? So this arrow implies that it is favored in forward direction. So that would be our work to basically solve a problem like this. Let's look at another example, okay? Where we're going to again complete the entire, we'll show the entire work for attempting a problem like this. Complete the acid-base equation and then analyze the strength of the two acids. So let's look at this as this set here. So let's say we have like that. Let's say that's what is given to us. So if you notice here, we have an alcohol here. Okay, this has a chlorine on the end here, on the end of the chain. And we have another molecule where there is a sodium and there's an oxygen and there's a 2-carbon chain. Okay, 1, 2 carbons. So again, going back to the basics, because you have a sodium and you have an oxygen, this is an ionic bond. So the charges are not shown. We are putting those in based on our understanding of bonding. This has to be an ionic bond. So even if it's not shown, I'm going to put it down. Okay, so we get a negatively charged species there. So now since we have a negatively charged species here, what that means is this is most likely the base. Okay, and then this other species here must be the acid. And again, there are several hydrogens here. There are hydrogens here, there are hydrogens here, and there's that hydrogen. And that hydrogen is going to be the strongest acid in this molecule, or the one that would have the highest tendency to behave as an acid. So I drew that out because I want to show my electron push. Very key. Okay, so now I have my acid, I have my base. I can show the electron push. The base abstracts the proton. Electrons here get pushed to the oxygen. And so I can draw whatever the resulting structure is. So I'm going to get O minus on that oxygen now. And then this part here, the base. Now, what's important to remember here is the base is not just this oxygen. The oxygen here is connected to that carbon, and that carbon is connected to that carbon, the other carbon. So this entire portion here is the base, but the oxygen is what's abstracting that hydrogen using its lone pairs. It has 3 lone pairs on it. Okay, this oxygen has 2 lone pairs on it. So now this oxygen here has 3 lone pairs on it, and so the oxygen uses one of its lone pairs to abstract a proton, and so what I will get at the end of it is going to be this molecule. That is what I get: CH3, CH2, O with a hydrogen. CH3, CH2, O with a hydrogen. Okay, so that would be our molecule, and sodium is going to be balancing the charge here. Okay, so we had acid. When it loses its proton, we get the conjugate base here. We had a base. When it accepts the proton, we get the conjugate acid. So we have the acid-base reaction at this point. The next thing we have to do is, again, determine the favored position at equilibrium, or favored direction at equilibrium. Okay, so for that, again, what we have to do is we have to evaluate the acidity or the strengths of the 2 acids. And we have 2 acids here. One is the acid itself, and the other one is the conjugate acid. Okay, and to evaluate to compare acidity of the 2 acids, we will evaluate the stability of the 2 conjugate bases. Okay, of the 2 conjugate bases. So for this first molecule, the conjugate base is here, and for that conjugate acid, its conjugate base is this base. Those are the 2 bases. So we are comparing Cl minus versus that. These are the 2 bases that we are comparing. And now we have to determine what factor are we going to use to compare their stability. There has to be some factor which is going to tell them apart. So if you look at it, the negative charge is on the oxygen in both cases. So that means the atom or the element effect would not work, at least at our first look, it doesn't seem to work. There are no double bonds. I mean, this negative charge is not allylic. And so that means we cannot do resonance here. And plus the hybridization is also the same. So if you just look at the framework here, it seems like there's a chlorine in one, there isn't a chlorine on the other one. So that means we are talking about induction here. So we can compare the stability of these bases on these conjugate bases on the basis of induction. So because there is a chlorine here, this conjugate base must be more stable. Okay, so this conjugate base here is more stable, and this base here is less stable. And since that conjugate base is more stable, what that means is this is a stronger acid, and this is a weaker acid. And then going back to the previous argument that we made, because this conjugate base is more stable, it is happy by itself, its tendency, now relatively, okay, its tendency to accept a proton is going to be less compared to the less stable base. So the base that is more stable is happy by itself. That means it is a weaker base, and this here is going to be a stronger base. And so it turns out in this set again, the two stronger components, the acid and the base, are on the left side or the reactant side, and the weaker components are on the products are. Now, this does not have to be the case all the time. So, but this is how it is in this particular equation. So we're going to say that the reaction is favored in the forward direction. So I've basically shown how I arrived at my conclusion. That's the reasoning that I used. There's induction, so this is more stable. Since it is more stable, it is a weaker base. Since it is less stable, this is a stronger base. Similarly, since this conjugate base is more stable, its corresponding acid is a stronger acid. And since this is less stable, its corresponding acid is a weaker acid. So that way we are able to work through this and we are able to arrive at a conclusion. So hopefully these examples would give you, basically guide you as you attempt problems like this. Okay, bye. Thank you.